In the previous lecture, we were able to understand how the bulk magnetization that is generated in the sample that you have precesses about the effective B field that is generated due to the external B naught and the applied RF field. The time domain signal that is detected in such a case was found out to be M plus, which is the signal along the transverse plane, transverse with respect to B naught, will be given by M plus of t will be equal to M plus of 0, which is the magnetization along the transverse plane immediately after application of the pulse that you had, followed by exp I omega t times exp minus r2t. This parameter, which is the oscillation of the magnetization in the transverse plane, helps you get the offset with respect to the applied transmitter frequency. And from this you would be able to get what is the Larmor precession frequency, and from this you would be able to get what is the chemical shift of the resonance that you're looking for by this given formula. Of course, this is denoted in ppm. We also alluded to the fact that the relaxation term results in the line width of the resonance that you end up observing. In this lecture, we will be taking a closer look at this offset parameter that helps you get the chemical shift. For most spectroscopists, we are quite familiar with the term absorption wavelength or absorption frequency. You can imagine chemical shift to be a similar parameter, however, is loaded with more information than what you generally get in an absorption or an emission signal. What you get with chemical shift is you would be able to probe the electronic environment of the given spin. For instance, we had seen the example of ethanol, where although the methyl and the methylene protons are both aliphatic in nature, the methylene protons ended up coming more downfield with respect to the methyl protons. So what results in such a discrimination of the frequency that we end up associating each of the spin with? This comes up due to the fact that the B field that is experienced, it gets reduced by a factor called shielding. The sigma parameter is called the shielding parameter. And for chemists, this is quite straightforward to understand that whenever you are having spins, you are actually also having sigma bonds that connect them to other atoms. Due to this fact, the diamagnetic electron cloud that is present ends up influencing the amount of magnetic field that is experienced by the given spin with respect to the external field B naught. And that is what is given by the shielding parameter. In its full glory, the shielding parameter is a rank 2 tensor, which is given by a 3 by 3 matrix of this sort. We will not be going into the details of why it's a rank 2 tensor or a 3 by 3 matrix. And this 3 by 3 matrix gives an idea of the electron cloud around the spin that is being investigated. Although we might naively think that the electron clouds would be symmetric in nature, this need not be the case for all the spins that we end up probing. For instance, let's say you have other carbon atoms attached to this given carbon. With electronegativity difference being 0, you can imagine, let's say, a sphere of electron cloud around this given proton. However, let's say we take some other example where this carbon is attached to a fluorine atom. In such a case, what ends up happening, the previously equally distributed electron cloud gets being pulled towards the carbon, and you might end up having something that is anisotropic. Instead of being a sphere, it could be, for instance, an American football. So therefore, what this finally results in is that the B naught field that you ended up applying gets perturbed to different extents. I'll draw an anisotropic electron distribution around this carbon just for the sake of visualization purposes. And you are able to understand that the diamagnetic electron cloud would therefore induce its own magnetic field, which will interfere with B naught and therefore result in such a kind of shielding. And this shielding parameter is once again a three-dimensional entity for every given spin that you're trying to look for. This shielding tensor can be diagonalized such that you get the off-diagonal elements as 0, sigma ZZ is greater than sigma YY is greater than sigma XX. So the frame that we go from here to here is a principal axis frame with respect to the shielding tensor that we have. In this given case, the one that we'll end up measuring in the isotropic condition will be the average of all these parameters. The shielding parameter in terms of isotropic measurements, which ends up coming up in all liquid or solution state NMR spectroscopy, will only measure the isotropic shielding, which comes up as the chemical shift. On the other hand, you could also determine what is the chemical shift anisotropy. Anisotropy is basically defined as the physical parameter when measured in different direction results in different values. This is what is defined as anisotropy. On the other hand, isotropy is one where irrespective of whichever axis you measure from, you get the same value. And it does make sense that in solution state you have isotropic tumbling, meaning that the molecules keep tumbling about any given axis, and therefore you have averaging that results in a scalar entity for the shielding parameter we are looking at. On the other hand, if you end up doing solid state NMR spectroscopy, this chemical shift anisotropy would end up coming, where we will try to see what is the difference that ends up coming between the largest value of the diagonalized tensor versus the other two values that are present. In solution state NMR spectroscopy, you are not going to end up seeing this. For the sake of completeness, I will also define the asymmetry parameter eta, which will be given by 3/2 delta sigma times sigma YY minus sigma XX. So once again, this will also not be seen in solution state NMR spectroscopy. The shielding parameter can be associated with the electron density around that given spin given by the Lamb formula. Rho of R is the electron density. Therefore, as the electron density is a function of the atoms that are attached or nearby to the spin that we are observing, the shielding parameter gets perturbed, and if the shielding parameter gets perturbed, then the field that is experienced by the given spin with respect to B0 also gets altered, therefore resulting in a range of chemical shifts for the given different spins that are present in your molecule. So I hope this gives decent enough introduction to chemical shifts. Just to give an idea, the proton shifts generally range between 0 and let's say 15 ppm. Tetramethylsilane, which has 4 methyl groups, provides a sensitive signal with reference to 0 ppm. Generally, aliphatic protons end up coming, let's say, in the 1 to 4 ppm range, 4 or even 5 ppm range, depending upon what moieties are attached to it. Water ends up coming very close to 5 ppm. And then aromatics end up occupying the significant portion of, let's say, 7 to say 9 ppm. Any aliphatic proton that are nearby to electronegative atom would end up also coming close to 6 ppm or so. Something like aldehyde and acids end up coming, let's say, at 11 to 12 ppm. You would also understand the chemical shift gets influenced by the formation of hydrogen bond, which we will see when we go towards biomolecules. Similarly, in the case of carbon, you have the spectral width that go between 0 to 200 ppm. You are able to understand the ppm scale. Carbon has larger range than that of proton. The TMS once again here, you would be able to see most of the aliphatic protons end up coming up to say 50 ppm. The primary, secondary, tertiary can be distinguished by that. And then aromatics and heteroaromatics would end up coming in the range of 120 to something like 1 times 150, 160 ppm. And then as you go much farther, you will have the aldehydes, quaternary carbons, the carboxylic acids and the amides and so on. This is a typical range that I am trying to give here, but we will take a look at specifics for biomolecules as we go forward. Fluorine has a much larger spectral width, which I request you guys to go and probe in detail. Now I'll give a few examples of online resources that are available for you so that you can take a look at chemical shifts that have been observed so far. You would find an excellent resource in organicchemistry.data.org, where all the chemical shifts for different spins can be found. I'll give a few examples here. So when you choose the proton shifts, this is an expansion between 0 to 2 ppm where different aliphatic protons that are present resonate at different frequencies based on what atoms they are attached to. So here you are able to see it's attached to a tin atom, and here it's associated with a 3-member ring. Here you are able to see it's a methyl group attached to phosphorus atom. These are methyl groups that are attached to an alkene moiety and so on. If you scroll this resource further, you would be able to see a detailed account of chemical shifts for different species for small molecules that have been observed so far, which is very well documented with literature references. Similarly, you can also choose the 13C shifts. You would be able to see here how spins that are present in different chemical moieties resonate at different frequencies, therefore making NMR an extremely powerful tool towards their analysis and characterization. The next resource that I'll be introducing you to is the Spectral Database for Organic Compounds, in short SDBS. Here, if you give any one of these fields, that is a compound name, molecular formula, even a molecular weight range, CAS registry number, or their own SDBS number, you would be able to see what all data is available with them. In particular, we are focusing on the proton and carbon-13 NMR. Let's give the example of pentane where we say C5H12. Let's say we search. It comes back with 3 entries here for pentane, neopentane and isopentane. Unfortunately, all of them have their proton resonances available in this database. So let's say we click this, which is pentane that I ended up clicking. The NMR spectrum is provided here, in addition to many different details that are necessary. In addition, you would also have the chemical shift information that is provided, and they say that these shifts are acquired from 400 megahertz. The next database that I would be introducing you to is called the Biological Magnetic Resonance Data Bank, in short BMRB. The BMRB database is for biomolecules where people look at peptides, proteins, nucleic acids, carbohydrates and things of that sort, and you would be able to even call a given structure that was solved using NMR for which you have chemical shifts. If you put the PDB ID, you will be able to get the information for that given molecule. This resource has a very nice tool here called the NMR Statistics and the Spectroscopist Corner, which we will visit right now. Under the BMRB chemical shift statistics, there are a lot of things that you could take a look at. You can take a look at the plots for protein data, for nucleic acid data, but for the sake of an example, we will be taking a look at the filtered set of data sets for the 20 amino acids. You are able to see that for alanine, the chemical shifts of the different spins are given. And you might wonder what these atom names are. Basically, H stands for proton, C stands for carbon, and N stands for nitrogen. If you would like to know what is HA and H, is that you will see soon that H is denoted for the amino proton, while HA is for the H alpha proton. Similarly, for C and Ca and Cb have their own nomenclature, where C stands for the carbonyl proton, Ca stands for C alpha, and Cb stands for C beta, and N stands for the amino nitrogen that is present. In case you are not familiar with this nomenclature, you would be able to find it from this BMRB database itself, where each of the nomenclature is provided here. This concludes the discussion for chemical shift. We will see how scalar coupling works out in the next class.